This is the electric fields homework, question 35. So first of all, define electric field strength. So there were 2 marks allocated to this part, so it is force per unit charge, but you also need to point out that we consider this as acting on a positive charge. So you could say force per unit positive charge. Next, state whether this is a scalar or a vector quantity. Because of how this relates to force, this leads to electric field strength also being a vector. And if you think about it, we represent electric fields with field lines with arrows indicating that they have a direction. Next, you are told that there are 2 point charges placed 80 millimeters apart. You are asked to find the magnitude of the force exerted on the 4 nanocoulomb charge by the -8 nanocoulomb charge. So because the question says magnitude, you don't need to worry about putting signs in for your values for charge. This is a very straightforward question, simply applying Coulomb's law to the situation. Just be careful to keep with standard units, however, because they have been used in the value of permittivity, so we need to have our separation in meters, which we have done here. So that leads to 4.5 times 10 to the minus 5 newtons. Next, you're asked to determine the distance from the 4 nanocoulomb charge to the point along the straight line between the charges where the electric potential is 0. Now, the equation for electric potential due to each charge is V is equal to Q divided by 4 pi epsilon naught R. And then you also need to remember that potential is a scalar quantity. So the potential due to each of the charges is simply added together, and we know that the combined effect is 0 potential. So we don't need to take into account any considerations of direction here. As I said, potential is a scalar quantity. However, the charge values do still have a sign. Looking back at the diagram, you will see that I chose to call the unknown distance that we wish to find x, and that is the distance from the 4 nanocoulomb charge to the point where the potential is 0. It can be useful to ask yourself in this situation where approximately you would expect this point to be. And if you think about it, you should be able to appreciate that it would be nearer the 4 nanocoulomb charge. So going back to the solution here, we simply have 2 expressions for potential corresponding to each of the 2 charges. So the 4 nanocoulomb charge divided by 4 pi epsilon naught x, and the -8 nanocoulomb charge divided by 4 pi epsilon naught multiplied by the remaining distance, which is the 80 millimeters take away x. So the sum of these potentials is 0. Now that does look a little bit messy to solve, but if you think about it, you can do some cancelling and you can very quickly make it look a lot more manageable. It doesn't matter which units we choose to work in here, so working in millimeters is fine as long as we're consistent. So I have been able to simplify back down to the value of 80. So then finally solving this equation, we see that 8x is 4 times 80 take away 4 times x, and that leads us to a final answer of 26.7 millimetres. Next, you are told that there is another point P in the diagram, which is the same distance from each of the charges. You're asked to draw arrows at the point P to show both the direction and the relative sizes of the electric field at P due to each of the charges. Following that, you are asked to then draw an arrow to represent the resultant electric field and label this as R. So going back to the diagram, you can see the identical distances here and here between each charge and the point P. And we're considering the direction and strength of the electric field due to each of the charges acting at point P. Well, clearly, since the distance from each charge is identical, the only other factor affecting the size of the electric field strength is equal to the charge itself. So since this charge is twice the other one, the strength of this field must be twice the strength of the other field. And then we just need to consider the direction. So imagine a positive test charge at P. It would be attracted towards the -8 nanocoulombs, whereas a positive test charge at P would be repelled away from the 4 nanocoulombs. So that gives us our two directions, and we just need to make sure that this arrow is twice the length of the other arrow here. So finally then, to draw the resultant, consider one of the vectors followed by the other in a vector addition, leading to the resultant as shown here. Next, we have another multiple choice question. So you are told that two horizontal parallel plate conductors are separated by a distance of 5 millimetres in air. So that's what I've just drawn here, the 5 millimetre separation and two conductors. The lower plate is earthed, so I've labelled that as 0 volts, and the upper plate is at 50 volts. You are asked to identify the electric field strength and the electric potential at a point midway between the two plates, so somewhere on this dotted line. Now, for parallel plates, the electric field strength is given by the potential difference divided by their separation. This would be a uniform electric field, so there is one value for the electric field strength, no matter where a point would be between the two plates. So that gives us a value of 1 times 10 to the 4 volts per metre. Now, you'll see that that value actually repeats 4 times, so that hasn't helped us very much. So we need to then also consider the direction of this electric field. So looking back at the diagram, we had labelled the upper plate as 50 volts and the lower as 0. So that's like thinking from positive to negative. This is more positive than that one. So the direction of the field is downwards. That now limits us to answers B and D. So finally we need to know the potential midway between the two plates, and since this is a uniform field, the potential halfway between them will be 25 volts, giving us answer B.